Welcome to the last lecture of my 5 lectures, and thanks very much for sticking with it. Today I'm going to talk about infinite groups because I guess cohomology of groups kind of splits between what I was talking about yesterday, cohomology of very small groups, P groups of order 32, 64, and people are interested in cohomological properties of infinite groups or larger groups. So can't resist but start with some applied topology. So if you have some object that you're interested in studying using applied topology, here I've got 2 knots somehow linked together, then in principle, if you look at the fundamental group of the complement of the 2 knots, you can do some cohomology calculations and calculate the number of times the red knot wraps around the blue knot, the winding number, the linking number. Well, I don't want to go into the details of that, but to do that, you have to kind of get a hold of the group, and in topology, really all topological methods give is something like a presentation of the group. So let's suppose that for some reason, we wanted to look at that link L using this fundamental group, which we found using discrete vector fields, whatever, to have this presentation. Well, as Heiko has told us, if you want the first homology, you can use Smith normal form and so on. You can use your presentation to get the first homology. But what happens if you want higher homology? So there's a bit of a problem because you have to construct somehow a space on which G acts, the space has to be contractible and so on. So what do? Well, there are various strategies. The presentation I'd rather think of as a 2-dimensional CW space. So the presentation consists of, it's a space really with a single 0 cell, 2 1 cells corresponding to the edges, and 2 2-dimensional cells corresponding to the relators. And then basic algebraic topology tells us that the space X is what I called yesterday BG, this contractible space EG with the action of G killed, if and only if the universal cover is contractible, and that's equivalent to saying, by Horevich's theorem, that you really want to check, does the second homotopy group of X, is it trivial? That's sufficient to say that in this case, the space X, this 2-dimensional space, would be a classifying space. So how could you go about that? So let's just see an example where it's clearly not always the case. I mean, for any finite group, it won't be 0. Let me just, for future reference, record this group before I wind it away. So this group has 2 generators, and it's got 2 relators. I think I'll start over here. One relator, x squared, which I'll record like this. And the other relator has 5 terms in it, and it's y squared x times y inverse x inverse. So in this example, let me convince you that the second homotopy group isn't trivial. What that really means is I have to show you that there are kind of no 2 spheres in the universal cover. So there's a theorem then that the second homotopy group of the universal cover is the same as the second homotopy group of the cellular complex itself. So let's work in the universal cover. I want to convince you that there are no 2 spheres in it, and that there are 2 spheres in it. And the best way I can do that is show you one. So I've taken copies of the 2 cells which live upstairs in the universal cover, so I have many translates of them. And you can see that they do, unfortunately, fit together nicely in a sphere, and that represents a non-trivial element in the second homotopy group. So that group, certainly I'd have to do some work. On the other hand, this group is finite of order, probably 6 or something, so I mean, I can use any of the methods from previous lectures. Well, we need some method for studying presentations of 2 complexes. So let me introduce this concept of the star graph. So given any presentation, and I have one there, let's construct a graph which has one vertex. So let's always assume that when I give a presentation, every generator which is there, also the inverse. So if x is there, I also have x inverse. so on. If y is there, also y inverse. Let's create a graph which has one vertex in any order, it doesn't matter, for each generator. So x is a generator, y is a generator in any order, y inverse is a generator, x inverse is a generator. Now, let's stick a single edge from vertex u to vertex v if the word uv inverse occurs once as a relator of a corner. And let's stick a double edge if it occurs more than once, if it occurs 2 or 3 or whatever. So if I go around here, I see, looking at this, maybe I use a different color. That is x followed by x. So I should connect x to x inverse. And this corner is similarly x followed by x. So I have to connect x inverse to x. It's undirected. This corner is x followed by y inverse, so I have to connect x to y. This corner is y inverse followed by x inverse, so that means I have to connect y inverse and x. This is what? This is x inverse followed by y, so I have to connect x inverse and y inverse. This is y followed by y, so I have to connect, this is a line. And my last one is y followed by x, so I have to connect. So you get a graph. Now let me label that graph, the edges of the graph, as follows. Well, there's the graph, so that was produced using GAP. Let me put some angles on each of the edges in this graph, subject to the following. So the corners then I'm going to assign numerical angles, and for each n-sided relator, I want the relator angle sum of that relator to be n minus 2 pi. So, for example, this relator here, maybe I'll use yellow, has n equal to 2 sides, so I want the angle sum to add up to 0. And let's insist that things are positive. So maybe I'll put a 0 there and a 0 there. And let me record it over here on that. I want here, I've got 5 angles. So I've got 5 minus 2 is 3 pi. Now, I can do this anyway, so just for simplicity, let's divide that by 5. Let me call that something like alpha. And let me assign alpha to every corner. So I'll record that on the graph. And that is an example of a labeled star graph. You don't have to divide the angles equally, but just for simplicity, I've done it like that. So here's a nice proposition which goes back to, it actually developed over time. There was a simpler version due to Sieradski, and then Gersten and Pride independently worked on it. So and I can't put a date, but it emerged in the 1980s. The following, it's very simple to prove. And it says this: if each loop in a labeled star graph of presentation satisfies that the loop angle sum is greater than or equal to 2 pi, then we've got what we want. The space is aspherical. So what does that mean? Every edge in this graph represents some corner of a relator. And if I have a loop going around, coming back to where I start, what that really corresponds to is a bunch of relators that I go around. And so what I'm saying then is that I want the sum of these angles to be greater than or equal to 2 pi. So how would you go about proving that? I won't prove it, but it isn't particularly difficult. To a vertex V, let's just define combinatorial curvature. So to a vertex V, let's define the curvature of V to be, well, just a, I mean, the 2 pi isn't really essential, it's just to kind of relate to standard geometry. Let's really let the curvature of V to be 2 pi minus the sum of the angles at V. And then it's it really is an exercise. I'm not going to do it on the board because I'll get stuck. but it's an exercise to show the following. If you take upstairs in your universal cover of X some CW complex, and let's, for the sake of argument, which has no boundary, so that there are no kind of, it's a manifold or something. If that has no boundary, then the sum, so this manifold will have a CW decomposition, and at each vertex I can ask for this angle. So for each vertex of my CW space, if you add up this combinatorial curvature, what you'll get is 2 pi times the Euler characteristic of M, which is a combinatorial version of the Gauss-Bonnet theorem. And so what you see is, if you want a sphere, the Euler characteristic of a sphere, I guess, is 2. So if you're going to have 2, you couldn't have all of these curvatures being negative. And that's where the angle sum comes into it. So you have to keep all of these curvatures positive if you want to get a sphere. So there's an example of a simple result that can be implemented, has been implemented in GAP. So I've taken the group from this link, input it into GAP as a finitely presented group, and then I say, is this spherical? And what's going on? Well, this process of adding in angles such that they all add up to the correct sum, you can really represent that as a linear programming problem. You can do it quite automatically. GAP actually calls Polymake to do it, but it's not a difficult, it's not a time-consuming procedure. And you can check, is it possible on the star graph to fill the angles in such that no loop has angle sum less than 2 pi. So in this case, we try it. It says fail, because it's not going to work. Nothing's going to work every time. So in this example, it failed. But there are many presentations of groups. So you maybe could devise a heuristic procedure for maybe splitting up somehow your relators into more relators, putting in a few more generators, and then fingers crossed, if you do that, it's still not an algorithm, but if it works, it works. So there is a function in GAP which just adds in heuristically more edges. And let's apply the same Pride, Gersten, Sieradski algorithm. Wow, it's spherical. So now we can calculate the homology because we have our classifying space. So you do. So this is, yes. So yeah. Let me. I've overstated. Let me say if there's a manifold, yeah. If there exists a manifold, so so I'm talking about a two-dimensional surface. If there exists a surface, thanks. That was a. Yeah. So you do need that, yeah, to get that result. To get this, yeah, because then if you've got a surface, they have to match up. Well, they won't have 3 faces in a surface. Oh yeah, no. Then you'd have no. Then you don't get this. You don't get that. Well, you have to say what you mean by the boundary, and it gets. So I guess I really mean M as a sphere is what I'm interested in. Yeah. So if your presentation is actually a presentation of a finite group or an nilpotent group, then you can use one of the procedures that I've talked about in previous lectures. Otherwise, you could just somehow try to find a useful representation. Now, this is where the mathematician comes in. You can't do this on a computer. And use that nice representation to build a contractible object on which the thing acts. And then apply the techniques of Wall's method. So here's a nice example. Suppose you've got these triangle groups that people talk about. So what's a triangle group? Well, yeah, I guess if it's not compact, yeah, I don't really know what I'd mean by the sum. Yeah, because I have infinitely many vertices, yeah. Yeah, but I guess yeah. So I'm really thinking of finite spaces, finite CW complexes. So they'll only be finitely many cells, so they'd be compact. Yeah. No, without boundary. So if there exists a surface, if there exists a sphere, I should have said sphere. Okay, I'm getting. If there exists a sphere M, yeah, in there, that's really what I want. So let's just look at the triangle groups. So the triangle groups, it's well known that they act on, well, it depends on the values of L, M, and N, but they act either on a sphere, on Euclidean space, or on hyperbolic space. And so how do they act? I think you take a triangle. So you take 3 points in your space, distinct points, non-collinear. You take geodesics between the points, so that always exists. And then you have some notion of angle, and you create an angle of pi over L, pi over M, and pi over N. And you call that A, B, and C. And A, B, C are rotations through, I guess it's 2 pi over L, 2 pi over M, 2 pi over N, respectively, about the various points. So you get an action of the group. Once you've got an action, you can ask for fundamental domains. So Wikipedia, fortunately, gave me some lovely fundamental domains. I've taken LMN equal to 237 and 235. 237 corresponds to the hyperbolic case. 235 corresponds to the spherical case. In each case, you can produce a fundamental domain. So, and in each case, what is a fundamental domain? It consists of 2 copies of this triangle. Is the fundamental domain. It's a rotation subgroup. So it's a black-white fundamental domain. Tessellates the space. The action is by rotation. So the space is contractible. Well, in the hyperbolic case, anyway, in the hyperbolic case. And so in the hyperbolic case or in the real case, what do we have? We can use Wall's method. We've got a space, a tessellation on which the group acts. It's a two-dimensional space, but there are stabilizers. Every vertex is stabilized by a finite cyclic group. But the edges aren't stabilized, and the 2 faces aren't stabilized. So you now got this space which is contractible. You're acting on it, and the stabilizer subgroups are rather nice. They're cyclic. So you do Wall's resolution, and I won't go through the details again, but you end up with an explicit free ZT resolution of Z, which is infinite dimensional, but it's periodic after a certain point. So that's fine. Okay, let's play the same game again. So the generalized triangle groups have a long history. I'm not, this was a student of Jim Howie, Gerald Williams, who came to do a postdoc with me. So he introduced me to these groups. Jim Howie has done a lot of work on these. They have a long history, but we thought, well, let's see if we can calculate the cohomology. And let me just say, first of all, that for various values of M, I don't remember this, so I'm going to look at my notes. You get some groups. So if L equals M equals 2, the group is just the dihedral group of order 4n. And if L equals n equals 2 and M equals 3, the group, seemingly, I checked this in gap, is A4 direct product C2. And if L equals M equals 3 and N equals 2, the group is of order 288. And then it's a theorem that for all other values of M, the group is infinite. So let's look at the infinite case. So for any of the finite cases, you could use any of the methods I talked about previously, because they're small finite groups. But for the infinite case, you have to somehow concoct something on which that group acts, something contractible. And one way to do that is browse through the literature. And Hagelberg, who is no longer in mathematics, he did his PhD and then kind of left after a year or two, but he produced in his thesis a nice action under that condition of the group on hyperbolic 3 space. So, so everybody knows then the hyperbolic plane is the Poincare model is the plane where geodesics meet the boundary perpendicularly, and hyperbolic 3 space we can think of it as a solid ball, and the geodesics meet the are semicircles that meet the boundary orthogonally. So that's hyperbolic 3 space. And in his thesis, he has a nice fundamental domain. There's a picture of it. What he does is he says, if you take a certain line, a geodesic, which I'll call Ly, and another one appropriately angled, which I've called Lx, and if you let little x act by rotation about Lx, and little y, the generator y, acts by rotation about the line Ly, you get you have to check, there's a fair bit to check, you get an action of the group on hyperbolic 3 space, and in the thesis, using Poincare's lemma for fundamental domains, he establishes that there is a nice fundamental domain, which is partially shown there. So let me go to 2 dimensions. I guess when you've got triangles, I guess consist of 3 lines. Is that right? So 3 lines could look like this, or they could look like this. They could meet at infinity, and actually in the 3-dimensional case, they could meet beyond infinity. It sounds very kind of triangles could look like that. That's a 3-dimensional picture. So these are finite triangles. Those are infinite, and these are exotic or something like that. So in this case, we've got an exotic tetrahedron. So it meets the boundary, and it meets beyond the boundary. So it's not compact. So we have a nice fundamental domain, but I'm not going to be able to get a CW complex because CW complexes, their cells have to be compact cells. So what we can do is a fairly standard trick. We can go to the dual. So here, I hope we can see it. I took it from our paper. I don't think I need to, actually. I wondered about that when let's just say Lm and N are greater than or equal to 0. Are greater than 0 or something like that. I'm not quite sure. When I was looking at the paper again in producing this, I was wondering why, but because I'm a co-author. So what do I mean by the dual? I've got this fundamental domain. Let's take the dual. So let's take one vertex in the center of each fundamental domain, and then 2 neighboring fundamental domains meet in a face. So let's join the 2 vertices by a geodesic line. So I've only drawn part of the line there. And then every edge of my original tetrahedron corresponds to a dual 2-dimensional cell. And I've drawn portions of it there, and that's it. You stop. So what I've drawn there is for part of the dual of this fundamental domain. Now, the group G acts on the fundamental domain, it acts on the dual. So let's look at the space formed by taking the orbit of all of the duals stuck together. So I've got this space which lies inside hyperbolic 3 space. But not only does it lie inside hyperbolic 3 space, I think I can see that it's homotopy equivalent, because I can see a homotopy. I can go out from beyond infinity and I can homotopy in this portion onto the flat 2-dimensional 2 faces in such a way that the infinity point, or beyond infinity, stays up a 1 cell, doesn't move out of the 1 cells. So I have a nice cellular homotopy of the delta onto the dual. And I'm taking the space then formed by infinitely many copies of the orbit of the dual, but those homotopies match together nicely. I guess that's what I'm trying to say. They match together nicely, so you actually get a contraction of hyperbolic 3 space onto the dual complex. But hyperbolic 3 space is contractible, so we have a contractible complex, which I'll call X. And then you say, well, let's write down the cellular chain complex of X. Now we're dealing with infinite groups. So you check that these 0 cells which correspond to the two cells of the original, have trivial stabilizer. The one cells in the dual have trivial stabilizer, but the two cells in the dual, which I guess correspond to the edges, they have stabilizers, cyclic groups. So we have a chain complex which isn't free, but it's very nearly free. So now we do Wall's trick, which essentially involves putting a kind of an infinite piece of a resolution up here, but these are already free. And you add everything together, and you get a nice periodic resolution for generalized triangle group for all of the L, M, and N in the hyperbolic case, and the Euclidean case. And a similar trick works for the spherical case. It's just you have to bear in mind that the sphere isn't contractible, but you can splice together any copies of the chain complex. So let me just say a thing about hyperbolic space or the Euclidean space. They're contractible. Both of those spaces are what I'll call unique geodesic spaces. If I take 2 points in the plane, there's a unique line joining them. It's not the case, I guess, a unique, what do I mean by a line? I mean a geodesic line. So that wouldn't be the case for a sphere, because if I take a point there and a point there, what's a geodesic on the sphere? It's a great circle, and there are many great circles joining these 2 points. So the circle isn't unique geodesic, but in the plane or in hyperbolic space, any 2 points are joined by a unique geodesic line. And using that fact, you can define the homotopy of the space to a point. So a homotopy kind of shrinks it, and that's the definition of the homotopy. H of xt just sends you an amount t. So you choose a base point x0 in your space, and h of xt just sends the point x a distance t along the geodesic line. So you've got a nice contraction. So based on that idea, Gromov and others said, well, let's kind of generalize this. So now there are some words in blue, boldened, so I'll explain the words. Let's suppose that we have a CW complex X. Okay, we got one. Let's suppose that it's piecewise Euclidean or piecewise hyperbolic. What do I mean? Well, let's say piecewise Euclidean. Every cell in my space, let's imagine that I can place a Euclidean metric on it in such a way that when 2 cells meet, the edge metric coincides so that the metrics match up nicely. And that's really what a piecewise Euclidean CW complex is, but hyperbolic or spherical, same definition works. And then the theorem is called Gromov's link condition, says that such a space is a unique geodesic space if the fundamental group is 0. So I'm going to need the fundamental group to be 0 because the torus always worries me. The torus isn't, the curvature is flat, but it's not a unique geodesic space because if I take a point there and a point there, there are 2 ways I can draw geodesics. So you can see why you'd have to put something about fundamental group. So, and the theorem is if the fundamental group, so the universal cover of the torus, of course, is the plane. If the fundamental group is 0, and the link, which I have to explain on the next slide, of each cell is a piecewise spherical CW complex. So that means it's a CW complex such that all of the cells can be given the metric inherited from the unit sphere. So everything matches up. And there must be no geodesic loops of length greater than 2 pi. So we've kind of seen this arising in the Gersten-Pride combinatorial thing. Then the space is a unique geodesic space, so it's contractible. If it's unique geodesic, you can contract it. So what's the link of a point? So here I'm going to kind of hand wave because that's nice. Let's take a Euclidean space. Let me take the plane tessellated by squares. Each square is a Euclidean square. What do I mean by the link of a point? The link of a point, I mean, I take all of the unit tangent, or Well, what do I mean by the tangent? I mean, I take all of the unit vectors around this, so that the link is a unit circle. But if I take an edge, what do I mean by the link of an edge? The link of a cell, or the link of an edge, I mean all of those vectors which are tangents, or unit tangent, and orthogonal to those tangent vectors lying in the cell. So I guess that would be a tangent vector, that would be a tangent vector, but I only want the orthogonal one. So in that case, the link is 2 points. 2 points is the sphere S0. So the link, if you think, it's actually better to think of 3 dimensions. Let's think of it, I can't draw it, but let's think of a 3-dimensional tessellation. Cubical tessellation, so I've got lots of cubes building up R3. The link of a point in X in an edge is a sphere. That's wrong. The link of a point in an edge is a circle. That should say a circle. Sorry, the link of the point is a sphere, but the link of the edge is a circle, and so on. So you've got this notion of link, and you can see there that the links, in each case, I've got a sphere, I've got a circle. You can imagine what I mean when I say there's a spherical metric. It's a piecewise spherical CW complex. And then Gromov's link condition says that you can do something, you can just add things up. If in the link there is no geodesic, there is no geodesic loop. So I mean, I may have a loop like this. This is a unit sphere. I may have a loop like that, and that's certainly, the length of this is less than 2 pi, but it's not geodesic. To be geodesic, I have to be on a great circle. And all of the geodesic loops in a sphere have at least, well, I have 2 pi actually, or at least 2 pi. So let me just use this link condition. And now I'm a bit nervous because I was sweating when I saw the previous speaker with his matrix. I think that's right, is it? Are people happy with my notion of a Coxeter matrix? So Coxeter groups, as defined then in the last lecture, they can be represented by diagrams or by symmetric matrices with some numbers, positive and non-negative numbers in them. For me, they can also have infinities. Okay, so I'm allowing infinities. And then you can think of the Coxeter group as being the group generated by reflections, but I'm not insisting that my reflections are orthogonal. So by a reflection, I mean something which fixes a hyperplane, but it doesn't have to be orthogonally reflected. So for such a group, well, in this case, the reflections are orthogonal, and what we can do is we can take, as we've done before, we can take a point in our space, R3. We can take the orbit of that point under the action of the group. The group is finite, so I get only finitely many points. I take the convex hull, and I get a nice CW complex, which is contractible, on which the group acts. Let's take a couple more Coxeter graphs. Do the same business, the same generators, reflections. I can still take a point in R3. I can take the orbit of the point throughout R3. Of course, it's infinite. But what am I really doing? I'm saying, well, let's just look at the finite parabolic subgroups. Let's take the convex hull for each of those finite groups. In this case, I guess you get a hexagon. And I'm actually taking the cosets, not just of the finite subgroup, I'm taking the convex hulls, not just of the finite subgroups, but of their cosets as well. And what you get is a picture, a 2-dimensional CW complex. And one more example. I drew these in the LaTeX package Asymptote. It's great fun. Let's put a couple of infinities in. So infinity means that 2 generators are not related at all. And you get a picture like this. But again, you get, I think it's hexagons and squares, and then nothing around here. But you still, because you're working in Rn, you still have this complex. The complex is piecewise Euclidean because each of the cells is a convex hull of a finite Coxeter group. So you have this complex. You can describe it group theoretically. So S are the generators for my Coxeter group, which may be finite or infinite. And then you get you've got this piecewise Euclidean complex, and you can describe it on a computer as follows. The k-dimensional cells, there'll be infinitely many of them, they correspond to the cosets of finite subgroups, finite parabolic subgroups. So you take a finite subset of the generator, set S, and then you just only consider the finite subsets that generate a finite group, and you take the cosets of those, and they correspond to the k-dimensional cells. The link can be, you can analyze this, I won't do it, you can analyze the link of a point, and in this case it turns out to be a simplicial complex. It's the simplicial complex consisting of all of the, if you think of it abstractly, S is a finite set. It's a simplicial complex consisting of all of those subsets of generators, where the subset is not empty, I guess, and the subset generates a finite group. That's a simplicial complex that you can really analyze pen and paper and test the link condition, which is what Mike Davis did. The date here, I'm not sure, but early 90s, really, I should have said. Used Gromov's link condition to observe that this Coxeter complex is contractible and admits an action of G with all stabilizers finite. So bingo, we can do resolutions. It's even nicer. Finite stabilizer groups are finite Coxeter groups. So if you can build a resolution for a finite Coxeter group by some formula, you can put it work recursively. And if you work recursively, you can recover using Wall's technique for free. That's an overstatement. Well, the following. For any Coxeter group, finite or infinite, there is a free ZG resolution whose free generators in degree K correspond to the, I'm not sure what I should have said, the sub K multiset. So a multiset, I'm allowing an element to occur twice. I could have an X and an X. I'd refer to it as an X squared. So I take I know what I mean by a set of size K. So a multiset is something with K elements, but the elements can be repeated. But I only want to consider those multisets of size K that actually generate a finite Coxeter group. And this is just using that complex and Wall's resolution, and you get this statement where I'm a little bit unsure of myself. So the method of the Concini and Salvetti is quite different, and they give an explicit, rather complicated, but explicit formula for the boundary. This is a recursive formula for the boundary, but on the computer, it doesn't seem to make much difference. I mean, on the computer, the boundaries, and what I haven't done is check that the boundaries are identical, but I can't imagine that they're different. It's the same number of cells. So, with 11 minutes to go, let me flick through this slide. So let's just look at finite Coxeter groups. And let's do the following. When I say you pick up a point V and take its orbit, if you take a point V which is not in any of the mirrors, you'll get one element of the orbit for each element of G. But if you move V into a mirror or into an intersection of mirrors, the group won't act faithfully on the vertices. But you still get an orbit of vertices. You can still take the polytope, and I've given you can actually, there is a combinatorial description which is very implementable on a computer of this orbit polytope. The details don't really matter. It's just that for a reflection group, even if you don't take your vertex in the center of a Coxeter cell, but in one of the mirrors, you can still write down theoretically what the combinatorial structure is. So why would you want to do that? Well, let's think of the Mathieu group. So I don't know much about the Mathieu group, but I know that it's 5-transitive. My co-worker, Mathieu Dutour, when we first looked at this, he said, let's just take an arbitrary vector. The Mathieu group acts on R24 by permuting basis vectors. If you take, let's take the vector 1, 2, 3, 4, 5 up to 24, take its orbit. The orbit is enormous, right? But the combinatorial structure of the polytope is very complicated. And it was hard to build on the computer. And then just actually playing around with M11 and so on, led us this. If you take this starting vector with just 1, 2, 3, 4, 5 followed by zeros, that lies in lots of mirrors of the symmetric group. So let's just ignore the Matthew group for the moment. If the symmetric group is a Coxeter group, and for the symmetric group, this lies in some of the mirrors, so you'll get a polytope which is described here. This is equal to this because the Matthew group is known to be 5 transitive. So the above gives you a combinatorial description of the orbit polytope for the Matthew group. And once you've got your combinatorial description of this finite group, you can do better than the Cartan. The Cartan-Eilenberg trick is fine, but it's like, I mean, I don't really think, if you just know things about the P subgroups and fusion, I don't quite know how you build a presentation for the group. Presentation is a little bit stronger than just knowing what the Zelo subgroups are and fusion. And likewise, resolution is a bit stronger than Cartan-Eilenberg. So we built explicitly up to low dimensions a free Z M24 resolution of Z with the number of cells, which won't be minimal, but it's in low dimensions. At degree 0, there's one orbit of cells, so its rank, the ZG rank is 1, and in degree 1, the ZG rank is 9, and so on. And then that was also used to compute the homology of the Matthew group, so we computed it 2 ways, get the same answer, so that's as best we can do in terms of proof. So I do have 8 minutes to go. I would like to say something, because I was asked about this earlier. Artin groups, so these are altogether more complicated. A Coxeter diagram gives rise to a Coxeter group, which I'll call WD. And as Gerhard has told us that its presentation starts off with the orders of the generators, x1 squared, x2 squared, x3 squared, all trivial. If you take your Coxeter presentation, this is just kind of playing with presentations now. If you take your Coxeter presentation and just ignore all of those relations, xi squared equal to 1, you'll end up with a different group. And the group you end up with is called an Artin group. So for example, this diagram here ends up with this presentation. Can we calculate its cohomology? We have to build a space. How about the following? If I look at my diagram D, if I look at these three, if I look at full subgraphs, if I look at these 3 vertices, they correspond to a 3-generator finite Coxeter group. If I look at these 3 vertices, they correspond to a finite Coxeter group. And when I mean full, if I'm going to include this vertex and this vertex, I have to include the edge between them. And once I include that edge, I get an infinite group. So the maximal finite groups, there are 2 of them. And if I build their Coxeter complex, this orbit, I get 2 nice polytopes. The edges of these polytopes in the Coxeter case, well then it's not quite the Cayley graph, because in the Coxeter group you've got x squared equals 1. But in the Artin case, we don't have x squared equals 1. This is really a piece of the Cayley graph of the group that I've drawn there. The edges are labeled by generators. So here's a conjecture. For any Artin group, you can do the following. You can take this space BD. What do I mean? I take these 2, in this example, I take these 2 polytopes, and any face which is labeled ZWZ equal to WZW, any 2 faces like that, I identify so that the arrows match up appropriately. And I end up with a 3-dimensional space in this case. And the conjecture, the K-pi1 conjecture is that that space is a classifying space, or in other words, its universal cover is contractible. Now, if we could prove the conjecture, we'd have a classifying space, and we could program in gap the chain complex. In fact, we have programmed in gap the chain complex, but the big difficulty here is not the programming, it's proving that the space that we've modeled the program on actually is contractible. So a fair bit of work has been done on this. So it started with Deline using hyperplane complements, proved a long time ago that in the case where your Coxeter diagram corresponds to a finite Coxeter group, then the K-pi-1 conjecture is known to be true. So Deline showed that whenever if you take the Coxeter graph AN and work out the Artin group, then Deline said, well, okay, this space that I've constructed will be n-dimensional or whatever, but it's a K-pi-1. It's universal cover, it's contractible. Appel and Schupp in the 80s, they looked at two-dimensional Artin groups. So a two-dimensional Artin group is, let's look at an Artin group with the following property. Whenever you take a pair of generators, no, it's the following. Suppose that no triple of generators generates an infinite group. So two-dimensional Artin group is one such that any triple of generators at the Coxeter level generates an infinite Coxeter group. And it was proved by Appel and Schupp that the K-pi-1 conjecture holds. Charney and Davis, more recently, in the Journal of the American Math Talk, proved a nice extension. And then just to end with a modest kind of, but totally different proof of Charney and Davis's result, this is a slight generalization, you get the following. An Artin group AD satisfies the K-pi-1 conjecture, the K-pi-1 conjecture holds, if for any infinity-free full subgraph D prime, the space BD prime, or the Artin group AD prime, satisfies the conjecture. So let me just give an example. Here is an Artin, here is a Coxeter diagram. If you take any full subgraph not involving an infinity edge, okay, so for example, I could take this. I end up with a Coxeter graph with 4 generators, and it's finite. If I take, in fact, I could take those together with this isolated vertex and that isolated vertex. That's a full subgraph. So I get a 6 generator, a 6-dimensional, but finite polyton. So that's an example of a Coxeter diagram satisfying this condition. And so you can run GAP and it will tell you what the homology groups are, but more than that, you know that it's correct because the K-pi-1 conjecture is known. So on that, I'd like to thank everybody for bearing with me, and I've enjoyed it. I hope you have, and I won't try to pronounce it, but thank you. Okay. Yeah.